All right. Well, welcome back, everyone. Hopefully, if as people are still plugged in or just getting back to their tables, back to their desks. We're gonna start with one other, one more of our our SMEs for the day. His name is Kirk Stueve. He currently works for Cirrus Precision Agronomy. But he's also been an instructor, a professor at St. Cloud State University. I'm going to let him give a more detailed introduction, and I'm going to pass it off to you, Kurt.
Appreciate the introduction, Tom. Am I coming through pretty clear?
Perfect.
Excellent. I think I'll just leave the video off. Sometimes I have challenges with the video. And so appreciate the opportunity to talk here. Excited to have a crowd this afternoon. As Tom mentioned, I wear multiple hats. And so one of my primary jobs is working in product development at Series Imaging. And so my specialty is dryland row crops there and finding practical applications of using imagery in agriculture. We happen to use fixed wing aircraft with cameras mounted on the bottom, but some of the principles highlighted by other speakers and applications and drones span across the divide here. I also farm corn and soybeans in western Minnesota, and as Tom mentioned, teach some courses at St. Cloud State University. So really fun space to be a part of. And my main goal here is to give a practical application or example of using imagery in agriculture, where we're tied and connected to a return on investment. In my opinion, that's been a real challenge in precision agriculture. We have all these images and pictures. They've been around for well over a couple of decades now, but we're still seeing kind of a lag in adoption. And I think that's because we've really challenged to connect the value of technology and imagery to the customer. And so for today's talk, I'm going to give an abbreviated. There we go. I thought it froze up on me. It's not a good omen. I'm going to give an abbreviated overview of VRE fungicide applications in dryland row crops. And so basically, I'm just going to give you a background and sort of set the stage for the problem and how imagery and technology could be used as a solution, and dive into some of the science, driving the value proposition, and also the economics and some of the engineering challenges with execution on the backside. So why VRE fungicide? Now, it doesn't matter if you're talking sugar beets, soybeans, or corn. There are myriad problems with diseases that generating billions of dollars in lost revenue every year across the conterminous United States and the world. And so that's well documented in the literature. You look at the University of Minnesota Extension agents, there's been a lot of work from sugar beets to soybeans and up into Canada as well. And so very well established that there are issues with diseases every year in trying to grow and raise crops. And so one of the key challenges here is obviously we have fungicides that we can use to mitigate disease pressure. But the problem is you have very narrow temperature, precipitation, humidity thresholds that determine whether or not you're likely to have a disease outbreak. And so if you're looking at Cercospora, in this case, it tends to favor temperatures right in that 68 to 79 degrees Fahrenheit range. Needs to be humid as well. If it gets colder than that, if it gets hotter than that, it's far less favorable for the development of the disease. And if it's dry, of course, you're not nearly as likely to have disease development. And so I'm going to keep this pretty high level. Don't get too bogged down in some of the more particulars here. And if you're looking at soybeans, white mold is a serious disease for the Northern Corn Belt. And so similar to what we're seeing in Cercospora, very specific weather conditions trigger severe white mold outbreaks. And so typically in this case, we're looking at a little bit cooler temperatures, 40 to 60 degrees Fahrenheit, moisture as well, shade. And so again, very, very, very specific criteria, in terms of your local environmental conditions, and dictates whether or not you're going to see a severe outbreak of white mold. And so that's one of the challenges. We have fungicide as a potential solution, but what we're seeing in treating fields the same with fungicide is variable results. And so I would just ask you to pay attention to the first row, non-treated control and yield. You can see the yield in the non-treated control for sugar beets in this case. Didn't matter if you're looking at 2005 to 2008 or 2007 to 2008. The yields are almost identical between the control with no fungicide treatment and different fungicides that were applied. And so you're easily looking at, $30 an acre in terms of an investment that may or may not pay off depending upon the year. Likewise, if we jump ahead to soybeans, we see something similar. We can. Again, the first row, number one, non-treated control. The final value, if you're looking at yield in the final column, 46.9 bushels per acre, statistically identical to all these different fungicides that were applied in an attempt to combat white mold. And so again, you're looking at risking upwards of $30 an acre or more to combat a disease that potentially might not pay you back. All right, so that kind of set the stage, for demand in the market, problem in the market. For the next, 4 or 5 slides, I'm going to set the stage scientifically for the field conditions and how variable they are. And so we're talking about microclimates here. And so, clearly the microclimates, local conditions in an individual field vary considerably from your standard temperatures recorded at the weather station. And so this is very well documented in urban forestry and ecology. It's also very well documented in like alpine treeline ecology. If you look at this graph, I'm sure none of you are surprised to see, if we're looking at temperatures, we have on the y-axis here in degrees Celsius, with trees, the gray on the bottom, of course, your temperature from the morning up until the midday and late afternoon, relatively stable. It heats up a little bit, but you just barely touch 35 degrees Celsius. Now, conversely, if you don't have trees, as we're all well accustomed to, we have a nice peak of heat around midday where we're up over 55 degrees Celsius. And so vegetation, canopy cover has a significant influence on your microclimate parameters. And as we just saw from all of those weather slides and some of the disease profiles, this can dictate whether or not a disease will occur. Now, if we shift gears a little bit from the urban environment to the mountainous environment here, we have another extreme example showing how vegetation can change the microclimate. And so in this case, on the y-axis, we simply have a transect from 0 meters up to 3 meters. And on the x-axis on the bottom, we have the time of day. And so during the daylight hours over here on the left, from 9 to 1500 hours, anything in red is hot. You're looking at 50 degrees Celsius or above. And so these red locations correspond to areas that have no vegetation. They're completely exposed. The green and blue areas on that part of the graph are much cooler, 20 to 29 degrees Celsius or less. Those areas have different degrees of vegetation. So we're seeing a significant influence of the microclimate on a short little 3-meter transect up in a mountainous environment. Now, if you jump to the nighttime, the opposite is true. Areas that were cold or hotter during the day are also colder at night. And so you're getting these extremes. And areas that were cooler during the day are warmer at night. And so that's the influence of vegetation on the microclimate conditions. Now, finally, shifting gears, I promised I would get through it, right? And it only took 7 or 8 minutes here. Tying this back to imagery, what gets me really excited as a remote sensing scientist and also as a grower and a potential consumer of remotely sensed images during the growing season is we have the capacity right now. It doesn't matter if you're using a camera from Series Imaging or Centera for that matter, but we can characterize the canopy quite well. We are very good at highlighting vigor. I happen to have a chlorophyll image up here, but it works just like the NDVI. Green is good, red is bad, white is open canopy. And so in this case, like we see in most fields, we're looking at a sugar beet field right here, but most fields, you're going to see a lot of variability from patches of open areas like we see in the white to these dark green areas where we have a thick, lush, dense canopy. And so the concept of variable rate fungicide applications is that we hypothesize that you're much more likely to have conditions suitable for disease development or for many diseases where you have that thick, lush, dense canopy. Now, why is that? Well, if I shift back and forth, I mean, we see some empirical evidence here. Here's a thermal image from the same flight on the same airplane collected at exactly the same time. I've converted all of these values into degrees Fahrenheit. And so anything red, you have temperatures 71 degrees or more. But anything that's blue, light blue, you're at 68 degrees or less. And so you can see most of the blue corresponds to areas that are dark green or green on the chlorophyll image. And so even if you don't have a thermal camera, you can still use canopy vigor, something as simple as the NDVI, as a proxy to characterize that microclimate environment in the field. Because where you have open or weak canopy, like you're seeing in these white and red areas on the chlorophyll, those temperatures tend to be hotter during the day. And we haven't been able to talk our pilots into flying at night, and I don't know if our processing team wants to process imagery from nighttime, but I would expect, and I'm sure most of you would agree, that these areas that are open to weak canopy would also be cooler at night. And so very similar to what we saw in that alpine environment a couple of slides ago. What does this look like in a graphical format? As you might expect, I just ran a simple regression analysis here. We have temperature on the y-axis and we have chlorophyll values on the x-axis. Most of your healthy, lush canopy over on the right side of the graph, where the chlorophyll values are around 0, they're tightly correlated with cooler temperatures. And as your chlorophyll values decrease down into these negative values, generally you see your temperatures increasing. And so we have a very, very solid relationship there between a very, very standard remotely sensed product based off in-season imagery, and we're relating it to the microclimate environment. Now, in this particular field, I work closely with a part of the season. You see the little marks here. These little hash marks, they're the only locations where we saw Cercospora early in the season. There was no evidence of Cercospora anywhere where the canopy temperature was hotter. Now, what's the opportunity here to act and take some action? Here's where it really gets interesting with my grower hat on and from the grower perspective. If we target fungicide applications on the best parts of the field, I have a real example here from one of my fields in western Minnesota. And so if we just run some numbers, in this case, we're looking at a more expensive fungicide called Endura. But if we apply no fungicide on areas with open canopy to weak canopy, the acres tally up to about 15 or 16 acres. And you still have that $7.50 an acre spreading cost if you hire it out. But if you shift to areas with average canopy up to dense canopy, your costs go up to $50 an acre, which includes the spreading costs and the costs of the fungicide. And so in this case, if you figure in $1 an acre for the cost of the imagery and making the RX, the return on investment is almost 900%. And so you got a really nice, solid value proposition. And we need more data, but the literature and some of our early analyses indicate that disease is not going to show up, especially white mold and Cercospora, where you have open to less open canopy, unless your broader environmental, macroclimate conditions would be conducive for it. And so there's a real opportunity here to tie imagery to value in a practical agronomic problem that we see out in the field. Now, the challenge is that all sounds great in theory, right? And so I have a PhD. We have a couple of professors on here. A lot of us live in theory, maybe too much of the time. There's still the challenge for execution. And so there's really not an issue in getting imagery in this day and age during the growing season, whether it be from a drone, a satellite, or an airplane, like the case if you're working with series imaging. And so that's the first part of the equation, relatively straightforward, especially if you're not dealing with more complex thermal products or something like that. And so I just have an example of a chlorophyll product over this Mary Hart soybean field that I pulled up in series imaging. And you can see it's quite variable. Open canopy in the white spots here, and some of these dark green spots, I can sometimes achieve 75, 80 bushel an acre beans if I can keep the white mold out of it. But certainly in the poor parts of the field, we have iron chlorosis issues. I'm wasting my money if I'm putting fungicide in those areas. I'm lucky to get 35 or 30 bushel beans. Now, in addition to the imagery, we also need equipment. And some of you may or may not have experience with the latest sprayers, but most sprayers right now used by cooperatives and growers at least have sectional control, where you have a monitor tied to RTK GPS up in the cab, and you can at least turn 8-foot sections or 10-foot sections of the boom off or on based off a prescription. Some of the newer sprayers actually have individual nozzle control, where you can turn those nozzles at the individual level off and on based off an RX. And so we really have the proverbial perfect storm, where the engineering on the sprayer side of the equation, that's progressed enough where it has the capacity to read in fairly complex equations and prescriptions from imagery during the growing season and acting on it. Then, of course, you would need to sync all of this information together and make it accessible to the grower and the agronomist. Any questions at this point? I'm just going to shift gears and pull up some software just for a little bit of fun. And so if you have questions, it's the perfect time to ask a question. Can everybody see? I have ArcMap up. Can everybody see ArcMap?
No, you still have your PowerPoint up.
All right, let me shift that here. How's that look, Tom?
It's good. It's perfect.
There we go. All right, and so here we've transitioned from the theory that I outlined before and sort of the idea and the value proposition to we're off in the weeds, getting our hands dirty here with execution. And so I just have a regular true color air photo in the background, and we have the farm for the local cooperative in the background. And I've been working with them to test this value proposition. And so what we did is I selected a test image from one of my fields over here in western Minnesota. You can see the main farm and a lot of variability, which is typical of what you see early in the growing season when beans are just achieving canopy closure. Anything that's light to moderate and dark green, you have good canopy. Anything red, orange, yellow is weak to non-existent canopy. And so I simply selected a test location out of this field and conveniently placed it next to the local cooperative. And so what you're seeing here is an RX file that was created from that imagery with the simple rule of applying fungicide at 20 gallons an acre in your light blue areas and applying no fungicide in the red areas. And so this is literally a test from just, about 10 days ago here to help prepare and ratchet up for the season. Now watch as I'm about to check the VRE fungicide as applied off and on. And so this is actually what was applied by a modern sprayer with a 120-foot boom and individual nozzle control. I think they were going about 5 or 6 miles an hour for this test. And so you can see, let me zoom in a little bit here. It's pretty exciting, and I know exciting is all relative, but I get pretty excited about this. As I check this off and on, I'm very pleased with the results that this 120-foot boom was able to mostly nail the execution and only applied product and just water in this case, but obviously it has the capacity to read in a fairly complex prescription and only apply product where it's called for at the level of an individual nozzle. And so as I'm checking this off and on, I mean, a couple of minor issues, you see a bit of overlap, but most sprayers are set such that the software ensures that the sprayer is engaged and functioning before it overlaps an area where product is called for. And so you'd expect it to be a little bit aggressive like we see right here. And so when I see results like this, I get really excited because it just highlights how exciting this space is. And it's a really interesting intersection between basic remote sensing. We don't need anything fancy for the imagery and the prescription here. We can use an NDVI to make the RX, and that is sufficient, as some of my slides from before documented, to highlight the differences in microclimate and make some zones in that RX and then bring that up into the sprayer and execute. And so the piece of this that I glossed over a little bit and wasn't sure how much time I'd have. So I have a few minutes, 5-6 minutes to wrap things up here. The challenge that most novice users have, especially if you look at agronomists and growers, is it's like, okay, they can access imagery from a bunch of different providers, could be satellite, aerial, drone, what have you, it doesn't matter. But there's still a challenge in converting that image into something that can be acted upon and used to deliver value to the customer. And so Series has a variable rate tool, and there are some other platforms that have tools as well, where you can actually, a novice user with very little GIS and remote sensing experience can go apply algorithms and make zones in a web-based platform and save it into a format that can be used in the sprayer. And so for the examples that I'm just going to walk through here to demonstrate this execution, I happen to be using just some bare soil imagery here, where we're making zones to pull out the lighter and darker soils, but the same principles can be applied in using this tool to make zones for soybean canopies or sugar beet canopies during the growing season. And so this first, oops, I better go back to my PowerPoint here. You would have caught me, right, Tom?
I would have, yes.
And so hopefully we're back to the PowerPoint now.
Yep.
All right, cool. And so I'll just wrap it up with the last 4 or 5 minutes here, walking through how this works. And so we're looking at just a regular true color imagery resolution over a pivot in North Dakota. You can see the lighter soils, the sandier soils, they appear quite light spectrally in this image. And your heavy dark soils with more loam and clay, they're quite dark in the image. And so if we jump ahead to the next slide, there's a simple create VRE map. And so that's a predetermined algorithm that is going to be applied through the web-based interface, through the app, to this image. And so you simply click that button and a little tool shows up on the right-hand side where you can pick your number of zones, zone size, and so you can change these different parameters. And you can hit create map. And once you create your map, you'll see a template of the potential prescription based off that image. And so you can see we have a series of different zones corresponding to the different soil types. Your dark reds and oranges are corresponding to the heavier soils. Your dark blue and light blues are corresponding to the lighter soils. You also have the capacity here to enter values for your prescription, that would be read and acted upon with the sprayer or fertilizer equipment, whatever the case may be. But again, the zones that you're seeing here with this VRA tool, they're simply being created with basic GIS algorithms using that true color aerial image as the target. Now, usually it takes some experimenting with the number of zones and zone sizes, but after you're done and you're happy with the results, you have a couple different options. One option is to simply save everything into a zip file. And so this converts your raster-based air photo to the vector format. And so in this case, it's being saved as a shapefile that's all zipped up. And that can be uploaded into most modern sprayers for execution, like we were looking at in with the as applied map in ARC map. And so I just walked through that process here. And AFS software is common precision ag software. And so I pulled up the same imagery and the RX zones made from that imagery. They look identical in the AFS software. And so most agronomists and some of your more savvy farmers would be very familiar with this software. Another option, and this is where it gets more exciting, we also have the capacity, and some other competitors do as well, but we're synced up with my John Deere. And so for any customers or agronomists, farmers, what have you, that have my John Deere, we have the capacity to send that prescription seamlessly right to the computer and the sprayer. And I did that last summer for a bunch of nitrogen trials down in Illinois and also in Nebraska. We're very, very exciting, fun, seamless process. Again, where we're using very, very basic remote sensing principles and imagery to connect with growers and agronomists in delivering value. And so for those of you that aren't familiar with my John Deere, here's a typical format. And here's, again, we see the exact same prescription in my John Deere ready to be used by a Y-drop applicator in this case. With that, I think I just maybe have a minute or so left here. I'm going to wrap it up there and would be happy to entertain any questions or feedback. Feel free to fire away, but I had fun talking about this and really appreciate your time this afternoon.
Hey, thank you, Kirk. We have a question from Michael. What is the average cost to fly fixed wing imagery, and what spatial resolution is needed for the VRA process? And I think we'd want to differentiate fixed wing from aircraft versus fixed wing from drone. And
Sure.
I'll let you try to tackle that.
Yep, no, appreciate the question. And so for a single flight, it's typically $1 an acre per flight. If you're doing more flights, you can get it down to maybe 60, 70 cents an acre or less. But obviously for a VRE fungicide application, you only need one. If you have one well-timed flight, that's great. That's all you need. So there's your $1 an acre right there. That's quite common. The spatial resolution is typically anywhere from 0.6, 0.7 upwards to 0.9 or 1 meters. If you get, we can provide a resolution with fixed wing aircraft, that's finer. But then you run into issues when you're making the prescription. Even modern equipment and modern sprayers, they don't have the capacity to respond at that very, very fine resolution. And so the sweet spot, and it's why we generally provide imagery at a spatial resolution of 0.5 to 1 meters, is because you can't act on that with the equipment yet. It's probably coming at some point in the future. But that's where we're at right now.
Thank you. I'm gonna, if there's any other questions for Kirk, feel free to either unmute your mic and ask the question or throw it in the chat. Otherwise, we're going to turn it over to Tom Biller or Steve. And thanks again, Kurt. That is awesome.
I appreciate it. I'll have fun, anytime talking about stuff like this.
All right, thank you, Kurt, and thank you, Tom.